Okay. So yeah, so let's okay. So if some of you can turn on your video, it would be great. Otherwise, talking to a black screen is not fun. Yeah, thank you guys. So okay, so let's last lecture was you know, there were a lot of definitions, right? And it was mostly definitions. We were studying this new thing for many of you, which is the Markov chains and so on. So let's do like a 5-minute recap from last lecture in terms of definition, so that we're on the same place. So let's see. So the first thing that we find, I'll do this very quickly and informally, less formal than last time. So we have a definition of a Markov chain, right? So we have some state space, it's a set of, say for now, discrete, finite, right? Okay. We also have a transition matrix P. And this transition matrix tells you the probability that if you are at a state X from the state space, you transfer to state Y, right? So for every X and Y in omega, P of XY is the probability of going from X to Y. Okay, so of course this means that the dimensions of P are determined by the cardinality of the state space. So P is omega by omega. Okay, so this is a Markov chain. That was the first definition. We went through a few examples and so on. The next important definition that we also spent some time with was this idea of a stationary distribution, right? So we wanted to see, okay, you start at some state X on the state space, and you start transferring from this state according to this transition matrix by flipping coins or picking random numbers and so on, and you move, and you want to know when say at infinity, when you've taken an infinite number of steps, what is the distribution of the chain, right? What is the probability distribution, in the sense that what is the probability that the chain is at different states of the state space, right? So we define this idea of a stationary distribution. And this distribution is a distribution pi that satisfies that pi times the transition matrix. If you view the distribution as a row vector and multiply by P, the transition matrix, then you also get pi, right? So in words, what this says is that these stationary distributions are distributions that once the chain reaches this distribution, it stays there, right? It's now you take one more step of the chain and it doesn't change the probability of being on any particular step, right? So that's the notion of a stationary distribution. And then we look at this fundamental theorem of Markov chains. That it gives you necessary and sufficient conditions for having a unique stationary distribution and convergence of the Markov chain to this stationary distribution, right? So, so what this says is that if P and omega, which is how we are representing the Markov chain, or omega P, I guess that's what I was doing yesterday. I mean, it's Read-on system, is irreducible. And remember, this means, this is just a fancy word for saying that the state space is connected. Right, in other words, we also saw this. We can view the state space as a graph where the vertex are the states, and then the edges are the possible transitions of the of P, right? Whenever P has a non-zero entry, we add a directed edge, right? And we say that the chain is irreducible if we can go from any state to any other state, right? Like if this directed graph is strongly connected. Okay, so that's the notion of irreducibility. There was another necessary condition that it was aperiodic, right? It kind of had like a different, kind of an odd definition that says like, well, if you're at a state and you record all the possible times at which you could return to this state, right? So you say you can return at time 2, you can return at time 5, you can return at time 7. And you look at the greatest common divisor between all of those, you get 1. So which means that there is no pattern, right? There is no this idea like you are always at this state at even times, or you are always at this state at times that are multiple of some other number that is no 1, right? So even though the definition is a little odd, we saw this required for bipartite graph, random walks on bipartite graph, for example. And it's kind of not a very essential one. I mean, it's essential for getting convergence and the unique stationary distribution. But it's a one that is, I mentioned that it's one that is very easy to achieve, right? Because you add a self loop to an irreducible chain, you are just a single self loop, and then you get a periodicity, right? So that's good, right? So, okay, so we have these two conditions, and then this implies two things. First, that there is a unique stationary distribution. Okay, and there is a subtlety here that even if there is one and it's unique, it may not be necessarily the case that you converge to it, right? But this theorem ensures that you do, right? So it also gives you convergence, right? So unique stationary distribution, and the Microchain converges to it, right? Okay, so there was one thing that I didn't mention last time. I forgot to mention this, right? That is this idea of how you find a stationary distribution. And that's sometimes, I mean, sometimes it's obvious, sometimes it's tricky. I think that in your problem set, you saw some conditions where it was very easy to get the stationary distribution. So we have this other set of conditions that are kind of weaker, right? They're easier to satisfy, but they're easier to check. And if they hold, then that implies that the distribution is actually stationary, right? So this is new. This is not, I didn't mention this last time. Maybe it was in your problem set, but there is this notion of reversibility. I wanted to plug it in here because it will be useful later. Reversibility. It's a new definition. So we say that P is reversible with respect to a distribution pi if for every pair of states we have this condition right. So this is sometimes called detailed balance conditions. Maybe you heard this. And they are useful because reversibility implies that pi is a stationary distribution. Right? This is actually, I think this was an exercise in your problem set, right? Maybe you can correct me. One of the DA. Boggy, this was the problem set, right? This was in the problem set.
Yes, I uploaded it. Yeah. I uploaded the problem set in Slack.
Right, but this is this was one of the problems, right? I think so. Okay.
Yeah.
But what is the point? The point is that this is sometimes, or actually many times, it's a lot easier to check that these conditions hold, right? Than checking that this condition holds, right? So it's a quick way of checking that a distribution is stationary. Now, it's not an if and only if. You can have chains with stationary distribution that are not reversible, okay? But this is a very desirable property because some of the theorems that we can prove about convergence and so on are a little stronger if we put this assumption of reversibility, okay? Okay, so let's see, what other definitions we had last time? So we have a notion of a stationary distribution, reducible, periodic, fundamental theorem, right? Then there was this idea of the MCMC, right? Which is a good thing. The MCMC method is a good thing to remember, since this is a course on the MCMC method, right? That this is a way of solving a family of algorithms for solving this problem of sampling from a complex probability distribution, right? So you have some probability distribution, it might be very complex, as we saw, like uniform distribution over the independent sets or the proper colorings of a graph and so on. The idea is that we design Markov chain that converges to pi. I'm going to use this for Markov chain from now on. Design Markov chain converging to the target distribution pi, right? There are some ways of doing this. There is some recipe and some cook-up examples that we know. But then a very important question here concerns the second step of the MCMC method, which is like run Markov chain for a long time, and output the state, right? And this is how Markov chain Monte Carlo algorithms work in practice. And I mentioned, like in theory, what we want to understand is what long time is, right? How many steps we have to repeat the chain, right? Is it polynomial in the size of the input? Is it exponential? Is it constant? Is it logarithmic in the size of the input, right? In practice, to some extent, you don't really need to know this, right? You can say, I'm going to run it for some long time, and then hope that this is good experimentally, and in many cases it is. And I think this is the fact that you don't need to understand the theory. To some extent, you need to understand the theory to deploy this in practice that make these methods very successful, right? But as theoreticians, we still want to understand and give some guidance on what long time means, right? And okay, so how do we mention convergence? Measuring convergence. This is the last definition from last time. Measuring the speed of convergence. There are various forms, various metrics. But the one that is the most standard one is this notion of mixing time, right? So the mixing time from state X, and if we tolerate some error epsilon, this is defined as the minimum time greater or equal than 0, so it's that the distribution of the chain and the stationary distribution of the chain, it's below epsilon, right? So, and this distance is measured in terms of total variation distance. Right? So remember that total variation distance is half of the L1, right? This is just 1/2 of the summation over, let me not use X, let's use something else, Y. Yeah, I guess I can show you a picture of what this looks like, because it's kind of intuitive. It won't look like, and this is also equal. You can check this, at least the exercise. That if you look at all the subset of the state space, and you look at the difference in probability between the probability that the chain is in that state versus the stationary measure, you get equality, right? So usually it's a good thing, like if you have two probability distributions, right? So, they say that these are the PDFs, right? So if you see what this is measuring, right? This is measuring essentially this distance. What total variation distance is measuring is this distance here, right? Between the two distributions, and then you have that, right? So it's half of the L1. Okay, so that was the epsilon. So yeah, it's important to recall that this is the mixing time from state X and allowing and tolerating only epsilon error. But in general, when we just say mixing time of the chain, we take the worst possible X and we fix epsilon to be some constant, right? So we say that the mixing time is the maximum over X in omega of T mix X 1/4. And the constant is a little arbitrary. The 1/4 is not that important. We can change it from some other constant and doesn't less than 1/2. I think strictly less than 1/2 is enough. One feature of the mixing time that makes it a kind of a peculiar definition is that we are picking the worst starting state of the chain, right? And there are some arguments for and against doing this, right? We need some standard. We do it like this. Mathematically, it's interesting, right? Because it's a look from it's a very strong guarantee. It doesn't matter from when you start. I can ensure that this converges, right? I can give you a guarantee that this converges. From the algorithmic point of view, as a practitioner, you say, well, why would I start from a bad state, right? If there is some state that's giving me a bad bound on the mixing time, right? Why would I start from there? That doesn't make much sense algorithmically. So if you have a good sense of what is a good starting state for getting fast convergence, you should definitely do that, right? And then the mixing time is not the right measure to look at, right? Okay, so those are the arguments, you know, for and against using the mixing time, but it's definitely the standard in the theory community too. I guess one of the standards. There is another one, but this is the main one. The next one I'll mention later. Okay, so this is everything we did last time. So are there any questions?
Sorry, I had a question.
Yeah, go ahead.
So in that last line, you have the max T mix of X and sorry, I misread it. It says 1/4, right?
Yeah, this is the 1/4. Yeah, sorry.
Okay, yeah, sorry.
So this is like setting an epsilon, right? Epsilon.
Yeah.
Yeah.
Thank you.
Yeah. And I think I mentioned this last time. You can once you get 1/4, you can boost this to any error that you like, essentially, and you pay very little. Just pay a logarithmic factor on the boosting that you want to get. Yeah.
I have a question.
Yeah.
You further explain why that 1/2 of that sigma equals the max thing.
So why this is true?
Yeah.
Yeah, this requires a little proof. I don't want to do it, but you should try as an exercise. It's not a, but it's so let's see, what intuition can I give you here? Yeah, okay, so it's I don't have a good see how can I give you with the drawing why this is true. Yeah, you should try this as an exercise. Let's not take this detour, okay? But yeah, it's an easy fact that you can check from this definition. Okay.
All right, thank you.
Yeah, so I'm just trying to see if I can show it to you here in this figure, but I don't think I. Right. One thing. Okay. So here is how you prove this. That you take all the x's, all the states where one of them is bigger than the other. Okay, and then you have some symmetry between that and the other side, right? And the ones that all the ones that are smaller. Right? So what I mean, like when this is, you look at all the x's that this is bigger than this. Right? And then you open this up and you can prove it. Okay.
Yeah, thank you. I'll think about it.
Yeah. Okay, good. So any other questions? Okay, so now the question is, and this is what we wanted to get at, like, how do we bound the mixing time, right? Looks like it's definitely an interesting problem, right? So you have this Markov chain, it's converging to some stationary distribution, and we want to say, look, how many steps do we have to take until we're close, right? At what rate are we converging to this limit, right? Which is the stationary distribution. And there are two types of techniques for bounding the mixing time. There are probabilistic techniques and there are analytical techniques. And by probabilistic techniques, well, I think there are two, but there's really only one, right? So one family of techniques is just use like very ad hoc analysis, and you try to understand the distribution of the chain after some number of steps with, manual calculations of these probabilities, and you somehow bound the total variation distance by getting bounds on the, right? What I'm saying is, like, you can try to get very precise understanding on this distribution. Of course, this is hard, and you can only do it for very simple examples. And for the cases that you can do it that they're not simple, it takes a lot of work, right? And if you see some work on Microchains from the 80s, if you look at some of the Microchain work from the 80s, this is what they were doing. We didn't have the techniques, so they were doing this, the kind of hardcore analysis of trying to get a handle on this. Right? The next one is the coupling method, which is quite powerful. And this is what we're going to discuss next. Okay, so what is the idea behind the coupling method? And of course, understanding this in depth requires a lot of practice, doing a lot of exercise, and spending a lot of time with this. But I think the idea is quite intuitive, right? Why it works is not that intuitive, but the idea of the coupling method is as follows, right? As follows. So suppose you have just some Markov chain, right? And you have some state space and you have some metric space, right? And we want to bound the mixing time of the chain, right? So we don't know what it is. So the approach here is going to consider two copies of the chain, right? Instead of having one copy of the chain moving over omega, we're going to consider two copies of the chain, right? And a coupling is going to allow us to advance these two copies of the chain at the same time, and we can correlate the move of these two copies any way we like. Okay, so I'll give you an example now. But the idea is that we're going to coordinate the move of these two copies of the chain, and the only restriction that we're going to put is that each copy has to be a valid realization. Right? So let me tell you what I mean by that with a very simple example. Suppose that you're looking at the line graph, right? Right? And now we're looking at the random walk on this line graph. By random walk, I mean if we're in a vertex, you have probably 1/2 of going to the right, probably 1/2 going to the left, right? But instead of considering one copy of the chain, we're going to consider two copies of the chain. Say one is here and the other one is here, right? And suppose that this is a very long path, right? So it continues. Okay. So so in one step, each of them is going to pick a random, it's going to pick a random number between 0 and 1. If it's less than 1/2, they're going to move left or right, right? So they could be uncorrelated, right? So one option is that no correlation, which means that they both move independently, right? Okay, and that's a valid coupling, right? There is no coordination, right? And the requirement that we have is that when we look at one of them, say the green one, the green one is moving with the right probability and so on. When we look at the red ones, it is moving. The red one is moving with the right probability. So this is true when there is no coordination. But this is also true if they use the same coin to move left and right, right? So suppose they use the same coin, right? Or the same random numbers. They use same random number. Right? So now what that means is that they're both here. We're picking the same random number for both of them. And if the random number is less than 1/2, then now they both move left. But if it's greater than 1/2, they both move right. Right? And again, you see that if you only look at the green one, right? The green one has the right law. It's moving with the right probabilities and so on. And so is the red one, right? So this is also a coupling. Right? The coupling, what I'm saying here, and I will define it properly in the next line and so on, is that if you look at the green or if you look at the red, they both have to have the right law. But now you see that the behavior is quite different. They are both coordinating the move and they are maintaining the distance as they move through the line. Okay? But this is not the only thing you could do. You can try more things, right? You can, for example, use the same coin, but do the opposite, right? So when the green one goes left, the right one goes right, right? So if green left, red goes right. And the opposite, right? If this one goes right, this one goes left, right? And again, now if you see the green one, it's doing the right move with the right probability. 1/2 is going to the left, 1/2 is going to the right, but so is the red one, right? So this is also a valid coupling, and it's correlating the behavior of the chain in a different way, right? So they're moving both apart or they're getting closer and so on, right? All of these are examples of couplings, right? And why this method is useful for bounded mixing time is because it will say, look, take two copies of the chain. Take any coupling that you like, design it any way you like, right? Try to make it in a smart way, right? And the goal is going to be trying to get the chains to get to the same state. And once the chain gets to the same state, that gives you a bound on the mixing time, right? So that's the whole method, right? So the name of the game here would be, okay, you have your Markov chain. You're going to decide how to coordinate the move of the two copies with the only restriction that each copy is a valid realization. And after that, we're going to try to bound the time it takes for the two chains to converge to the same state. Once that happens, that time gives you a bound on the mixing time. Okay? So let me state off that, and then we'll come a little bit more and look at some examples. So let me define a coupling now. So the coupling of a Microchain let's call it M omega B is another Microchain. Let's call it XT YT, right? This is going to be a sequence of the Microchain. And this Microchain is going to be on the product space, right? On omega times omega, right? Because there are two of them, right? So you can look at both states, right? So it's a Microchain on this. And what it needs to certify is that each copy, XT and YT, is a valid realization of M, right? So how do we ensure that? We say that probability that XT plus 1 equals X prime, given that XT is X and YT is Y, this is the probability of going from X to X prime. Right, this means that the transition probability for X are the right ones, and we also need the same for Y, right? The probability of YT plus 1 equals Y prime, given the state of the chain at time T, is just the probability of going from Y to Y prime. Okay, so, and remember that what this means with words, right? I mean, this is what I've been saying. It's good to emphasize it, that if you look at the sequence X0, X1, X2, just at X or just at Y, these are both instances of M, right? Both valid realizations. And as we saw in that example, we can coordinate the move between X and Y any way we like, right? So this is the definition of the coupling, and let me now write the coupling lemma, which is how we bound the mixing time using coupling. So we consider any coupling, of M and suppose that we find some time T that ensures that the probability that XT is not equal to YT, given that, okay, so this is for every starting state. So given that we started X from X and the chain Y, we started from state Y, if this is less than 1/4, then the mixing time is bounded by T. Okay, so any questions about the statements of the lemma?
Just to clarify, is a coupling a particular scheme of correlating these two different Markov chains, or is it two particular instances of a Markov chain?
It's a particular way of correlating two instances of the Markov chain. Right? Any way that you can correlate them, that meets, I mean, it needs to satisfy these two conditions, the way you correlate them. But any way you correlate them that satisfies those two conditions is a valid coupling. And what this coupling lemma says is, well, for any coupling, right? Any correlation scheme that you define, right? You get a bound on the mixing times if you can get a handle on this coupling time, right? The time it takes for the two chains to get together. Right? Now, of course, it's finding good schemes. It's usually the hard part, right? Sometimes it's easy, sometimes it's obvious, but in general, it's hard to find. Even though we know that there is, I mean, there is this theorem that would say that there is always a good one, right? Finding it, it's hard, right? And it has to, we need to, because it's an algorithm, right? So the existential proof is not going to be very useful for us, okay? So that's actually both the, the power and the drawback of the coupling lemma. One is that you know that there is one that is good. The second, that's a good thing, right? The bad thing is that finding it is usually quite hard. Right? Not usually, but in many cases, it's quite hard. And I mean, it's very common that you come up with some scheme that you say this is a good scheme. You code it and you see that the convergence time is quite fast, right? But then we cannot prove it because it's hard to analyze, right? So it's a little bit of a balance there between things that we can analyze with things that are actually fast. Okay, so yeah, the proof is quite simple. Let's do it. I mean, it's a kind of one of the key things that you see in this. I mean, I guess that the theorem statement is more important, but the proof is simple enough that we can do it. Okay, so any other questions before we do the proof? Right, so you take a set, let's take some arbitrary set in omega. Let's fix some starting state from X. This is an arbitrary set, arbitrary starting state. And let's assume that there is a copy, another copy of the chain that we're going to couple with X. But let's assume that the starting state is going to be from the stationary distribution, right? So this is kind of a special pair of microchains, right? of instances of the microchain. For X, we're going to allow any starting state. For Y, we're going to pick a sample from the stationary distribution. I mean, that's a hard problem in general algorithmically, but not mathematically, right? We can definitely assume that Y0 has that distribution. Right? So this is going to be our starting setup, and let's look at the probability that X, right, let's look at this. Right, so let's look at P, the distribution of the chain at time t, starting from X, and let's look at the probability that is in A, right? So the point is that we're going to try, right, remember, we have to bound the mixing time, right? So what is let's not look, this is our assumption. We know that this holds, right? And what we want to bound is that at that time, when this holds, the total variation distance is small. And that's what we want to say. We want to say that at the time, let's say this quantity is the one that we're going to use for the total variation distance. We want to say that this is a small. Okay? So, of course, what we're going to do is, that's why we're starting with this, right? We're going to try to bound this. Okay, so what is this? Well, this is the probability that the chain, right, is xt is in it, right? And there is going to be the extra condition in there that the chain starts from X and so on. I'm going to avoid that, right? So there is some condition in here. This is, we're going to condition that x0 is X and so on, but it just gets, I will have to write that in every line. I don't want to do it. So just assume that that is there, right? Okay, so what is this? Well, this is lower bounded, definitely by the probability that xt equals yt and yt is in A. Clearly, right? So if the two chains are if the two copies xt and yt are equal and yt is in A, then xt is in A, right? Of course, xt can be in A without being equal to yt, so that's why this is a lower bound. Okay? So now this is equal, we negate that, and this is equal to 1 minus the probability that xt not equals to yt, or yt not in A. Okay, and now we're applying a union bound. You guys familiar with that? right? So remember, probability of A or B is bounded by the probability of A plus the probability of B. So we apply that to this quantity here, that is a negative, so you get a lower bound. So this is 1 minus the probability that xt not equals to yt minus the probability that yt not in A. And now this is equal to like this 1 with this, and this is the probability that yt is in A minus the probability that xt not equals to yt. Okay, so we're almost there. So this, remember, y0 started from the stationary distribution. And by the definition of the stationary distribution, that means that after we take one step of the chain, y1 also has a stationary distribution. And so does y2, y3, and so on. Y will always have a stationary distribution. In particular, yt here has low pi, which means that this is equal to pi of A, right? This term here is equal to pi of A. And from the assumption, we know that this is less than 1/4. That was the assumption of the coupling, right? So this is at least pi of F minus 1/4. And now this gives us kind of the bound that we want, right? So we have that 1/4 is greater than pi of A minus PD of X. And this is essentially all that we need. Once we get this bound, is maybe now you believe me and I can stop the proof here, or I can finish. It's just 2 or 3 more lines. But the point is, like, you see, we're getting a 1/4 bound here for any set A, right? For any set A, we're getting this type of bound, which is, remember, this difference that we have here, right? For any set A, except the absolute values, right? We're getting the bound that this is less than 1/4. So the rest of the proof is just saying picking the right set and dealing with the absolute value, right? So let's just do it. So if you take the set A to be the set that maximizes the absolute value, right? We choose A like that. Take it like that. And then if, one option is that pi of A is greater than this, then we're done, right? Because the absolute value is going to be exactly equal to this thing that we know that is less than 1/4. So the total variation distance is less than 1/4. So done. And so let's say with equality here, and if you have the opposite, well, all you have to do is look at the complement of the set A, because if this is the case, then what we have is that pi of A minus this, right? This is equals to this. And of course, we don't know that this is less than 1/4, but this is going to be equal by complementing both sides. It's going to be equal to PA complement minus PT of XA complement. And by applying this here, this holds for any set, right? So it also holds for n complement. So this is less than 1/4. And then we're done. Okay, so this is the full proof. Okay. Okay, so if you didn't follow the proof, I bet that most of you follow it, but if you didn't follow it, that's fine. Remember that what we want to do here to bound the mixing time, pick 2 copies, correlated with some scheme, bound the time it takes for these 2 things to get together. Okay, that's the one thing to remember of the coupling lemma. Let's look at maybe one example, because I also want to tell you about the second method. Okay, so let's see which one is nicer of the examples I have here. So maybe this one is nicer. So let's look at an example for the coupling method. Okay, so let's look at the random walk on the hypercube graph. Let's say n-dimensional hypercube. So you guys familiar with this graph? So this is the graph where n is the dimension. So the vertices corresponds to all the binary strings of length n, right? So V is all binary strings of length n. And then we put an edge between two strings that differ on only one bit, right? Put edge if two strings, two vertices differ in one bit. Out of curiosity, have you guys seen this graph before? I mean, it shows up in computer science in many areas, right? So, okay, so just okay, so 2 dimensions, the graph will look something like this, right? So you have all binary strings, and this is how you connect them. 3 dimensions, it's 2D. 3D looks more something like a cube, right? And now you have all binary strings of length 3. So this would be like 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, and you know, now you can complete, right? So this one would be 0, 1, 1, this one would be 1, 0, 1, and this one would be 1, 1, 0, this one would be 1, 1. Okay? So that's the 3-dimensional hypercube. Okay, so now we have that graph, we can define it for any n. Now we look at the random walk on this graph. Okay, so you're at a vertex, you pick a random neighbor, and you move there, right? So what is the random walk? Well, one way of writing what I just said is that we pick a random coordinates, say I in 1 through n, uniformly at random. Right? We also pick a new value for that coordinate. We pick a new bit, right? We pick b in 0, 1, right? Uniformly at random. And then we flip the way this is how you usually write uniformly at random. And then we flip that bit, right? We flip, okay, we don't flip it, we set the bit at position I to b. Okay? So that's the random walk on this graph. So notice how this chain is lazy, right? Because when you pick a random coordinate, any coordinate, there is probably 1/2 that you pick the same bit that was there before, right? If it was a 0, it's probably 1/2 that you set a 0, which means that you don't move, right? So with probably 1/2, this chain doesn't move, and with probably 1/2, it picks a random neighbor. When that happens, we say that the chain is lazy. Theoretically, it's easier to consider these lazy chains because they're already aperiodic and so on. They're nicer to work with, and it doesn't really change the behavior. Okay. So now suppose that we want to find the mixing time of this chain. Right? Anyone knows what the answer is for the mixing time?
I'm going to guess n, the number of dimensions.
So you guess is on the right ballpark. So you're saying that you need to update every coordinate, right? But there is a subtlety here, right? Since we're picking the positions where you update at random, right? You would need to wait until you actually update every component, right? It's not really going to be n, it's going to be a little bit more than n because there is this extra delay. But the intuition is right? It will be n log n, okay? And how do we prove that? Well, we design a coupling and bound the coupling time. And in this case, it's not that hard to do, right? So here is a coupling. What is the most natural coupling that you can think of, right? Suppose that you have two different copies of the chain and 2 different vertices, and we want to coordinate the move. And remember that these are the moves, right? Any suggestions on what to do?
Could we choose the same bit and set them to the same value in the 2 different
Good, right? So we pick the same bit. We're going to pick the same position. Actually, let me just write that because that's exactly what we do. We're going to pick same position and same random bit, right? And remember, this makes a lot of sense, right? Remember, our goal is going to coordinate the two chains so that they get closer together. And in one step, we're flipping one bit. Well, if we're flipping one bit, let's fix it so that they get the same bit at that position, right? So this is the coupling, right? And this coupling, you know, the key property here is that after updating, let's say, position I at time t, we have that xt plus 1 in I is going to be equal to yt plus 1 in I. And not only that, this is going to be preserved now forever, right? Because once they agree in the coordinate, if we keep running the coupling, even if we update that coordinate again, they're still going to match, right? So once we fix one bit, it's fixed forever, right? So actually, what we get is that xt of I equals yt of I for all t greater than t. Okay. So this suggests that if we want to check, we want to bound when xt equals to yt, all that we need to do is wait until all the component has been visited, because if that is the case, then they are equal, right? Once we updated every component, every coordinate, then they're going to be equal. That makes sense? So let's write that, right? So let's look. We want to bound the probability from the coupling lemma, right? So this is the, remember, this is the condition. In order to apply the coupling lemma, we need to bound this, right? Assuming arbitrary initial states. We want to say that this is less than 1/4, right? Well, if we let t to be the minimum time so that every coordinate has been visited, so minimum so that every coordinate has been updated, right? The only way that we're going to get a disagreement here is if this little t is smaller than capital T, because we know that at capital T there is equality, right? So this is going to be bounded by the probability that, you know, let's say tau is less than t, right? That makes sense? And now we can bound this by Markov inequality, right? Remember, Markov inequality gives you, we're looking at the probability that a random variable is bigger than some value is going to be bounded by the expectation of t. Right? So remember, what we want to do is bound this by 1/4. So it's sufficient to write this by 1/4. And to bound this by 1/4, all that we really need is to find out what this expectation is, because once we get the expectation, whatever that is, we're going to set t to, you know, something that will make this more than 1/4, and then this t will give us a bound on the mixing time. Right? So what is the expected value of t? Anyone knows? Because maybe some of you knows what this is, right? So here is the problem that we're really looking at. Let's abstract from a little bit from this point, right? So you have a collection of n elements, right? And every time you're getting a random element from this collection, right? So you have one through n. So you pick a random number, and then you pick another random number, and then you pick another random number, right? How many times you have to pick until you choose everything, right? Have you seen this before? This is called a coupon collecting problem. Right? It's one of the things that you should remember when you're doing analysis of randomized algorithms is this coupon collecting problem. Okay, so it's a very, very important primitive in the analysis of randomized algorithms. If you can imagine that this shows up anywhere, And it's called like the coupon collecting because you assume that you have n coupons that comes like in a box of cereal. Every time you get a box, you get a random coupon. How many boxes you need to get? The answer is n log n, right? This is equal to actually theta of n log n. We understand this very well. The proof is 5 or 6 lines. I will not do it because it's not much time. It's in the notes. I think at some points the TAs will give you the notes. You can check the proof of the coupon collection problem there. Remember this. This is a kind of an important. This is an important, useful thing that you can use in an analyzing randomized algorithms. Okay. Well, this means that this expectation is n log n, right? And so once we know that, right, then this probability here is going to be bounded by some constant times n log n over t. That means that if we pick t equals to, let's say, 4 times that constant times n log n, we get the bound that we like, right? We get that this is less than 1/4. And if that is the case, that means that the mixing time is going to be bounded by 4c n log n, and this is just order n log n. Okay? Questions?
So I think in this case, we chose a sort of helpful coupling scheme where the 2 points are always moving toward each other. But I think another valid coupling scheme was where we always set the bits to opposite of each other. And so that the two random walks can never collide. But we don't need to consider that case because we only need a single coupling scheme to bound the entire.
Exactly.
Okay.
You just need to find a good one. There are going to be many, actually, most of them are going to be bad, right? I mean, you can be very creative and make these things never collide, or taking it, they will take a long time to get to the same place, right? But you only need to find a good one, and that's enough. That's the whole beauty and part of this thing is that you know that, and we know that there is a good one, right? I haven't shown you a proof of that, but we know that there is a good one, and you need to find it, right? And sometimes it's not possible, right? But you only need to find a good one. Any other questions? Okay, so I had another example, but I'm going to skip it. You can check it in the notes. This is the random walk on the cycle. So you look at the random walk on the cycle, and you can again coordinate the moves so that the random walks get closer together. And it's kind of an easy exercise. So you can try it as an exercise, but it's actually in the notes too. So you can check it there. And the reason that I want to skip it is because I want to make sure that I have at least 15-20 minutes to tell you about the second way or family of techniques that we have for analyzing Markov chains. And these are called analytical techniques. And there is more variety here. But I'm going to show you the one that is 90 or 95% of the analysis. You should use this type of approach. And it actually involves looking at the eigenvalues of the transition matrix, right? So let's see. So here is a quick fact. And again, I think I have to skip all the proofs, but some of these are in the notes too, right? So we're going to assume that P is ergodic and reversible. Remember, ergodic means irreducible and aperiodic, right? So this is a necessary and sufficient condition for convergence to pi. So it's ergodic and reversible. With respect to pi. Okay, so the eigenvalues, P is a square matrix, right? So it has eigenvalues. The values of P satisfy the following. First, it's fairly easy to check that 1 is an eigenvalue. And actually, 1 is the largest eigenvalue. And then all other eigenvalues are between 1 and -1. Okay, so it's not equality here. Okay, so this is an easy fact that says that if you look at the eigenvalues of P, the first one is going to be 1, and all other eigenvalues are going to be between 1 and -1. Okay? And yeah, so again, check the notes. This is two-line proof. But here is the interesting quantity, and this is perhaps a little surprising to some of you. We're going to look at something called the Spectra Gap. Okay, so let's call it gap of P, and the Spectra Gap of a matrix is the difference between the two largest eigenvalues, right? Between the largest eigenvalue and the second largest eigenvalue in absolute value. So this is 1 minus, look at the maximum between the absolute value of lambda 2 and the absolute value of P. You can check that when the matrix is lazy, these eigenvalues, all the eigenvalues are between 0 and 1. They're all non-negative, right? So then the spectral gap becomes 1 minus lambda 2. Okay? But in general, if we don't assume this laziness of the chain in every state, then this is how the spectral gap is defined. Okay, so this is just a definition. And what is surprising, at least a priori, what is surprising is that this quantity captures the mixing time. It gives you a very good bound on the mixing time of the chain, right? So here is a theorem. The mixing time of the chain is bounded by the inverse of the spectral gap, so 1 of the gap, times some factor and it's also lower bounded by some constants, essentially by the inverse of the spectral gap. Okay? So here, pi mean is something that depends on the stationary distribution, is the state with minimum probability. The probability of the state with minimum probability. Okay, so this is the other important theorem, right? Think of it as another tool. In addition to the coupling lemma, we have this other tool for bounding the mixing time, right? So you see, if you have your matrix P, and you can compute, the first eigenvalue is 1. If you can compute the eigenvalues, let's say even the second eigenvalue and the smaller eigenvalue, even if it's if you make this chain lazy, you only need to consider the second eigenvalue. The inverse of that difference essentially captures the mixing time, right? So you have 1 over gap up to constants on the left-hand side, and 1 over gap up to some other factor, right? But in many cases, this factor is not bad, right? And remember, we're taking logarithmic or logarithm of that. So this could be like let's say when we're doing dependent sets, this could be like exponentially small. And when you take logarithm of that, you get actually a polynomial factor, right? So in many cases, this is small enough that this is a very good bound, right, on the mixing time, if we manage to bound the gap, right? So you see, unlike the coupling approach, there is really no design aspect in this approach, right? You have your matrix, compute the eigenvalues, right? The problem is that we're talking about exponential size matrix, right? So we can't go ahead and really compute them, right? And these metrics can be quite sophisticated, right? So the problem of computing these eigenvalues of these metrics is actually quite hard. And if we want to do it directly, well, you can do it for like the random walk on the hypercube, we can do it, the random walk on the cycle, we can do it. And that's, maybe simple chains on the line, we can do it too. But in most cases, we cannot do this calculation directly, right? So that's why we have yet another variant to bound the eigenvalue. By the way, are there questions here about the theorem before I move to the next? No? Okay, so bounding the eigenvalues, right? As I was saying, it's not an easy task, but we have this combinatorial way of bounding the eigenvalues, that is this notion of conductance, right? So let's see. So the conductance, so this is the definition, the conductance of a set, of a subset of the state space is defined like this, is a conductance. So we look at, we sum over all the elements in the set, we look at all the elements outside of the set, and we look at the probability of the chain transitions, essentially, from S to outside of S, and we look at the ratio of this with the probability of S, right? So this is the conductance of S. Okay, so if you think about this, like if you think for a moment about this, to get a rough idea what this is, right? So you have a set, right? And this here, the numerator here is looking roughly at the probability of escaping that set. The chain, the probability of the chain can move from X to outside of S. And you look at the ratio between the escaping probability over the whole mass of S, right? So this is kind of measuring how good the chain is at escaping this particular set S, right? Then we define the conductance for the whole chain of the minimum conductance of any small set. Or the S such that the probability mass is less than 1, right? And why is this useful? Because you would think that if you have some set, some small set of the state space that has small conductance, right? It means that the chain has a hard time escaping this small set. And if the chain has a hard time escaping a small set, it means that when you're doing the exploration, you're kind of stuck in this small part of the big state space. That should delay your mixing time, right? The chain needs to go ahead and walk and explore the whole thing, right? So in fact, this is true, right? This is called Chig's inequality, but in the context of Microchain, this was proved by Jerome and Sinclair. And it's like 89 or 90 or something like that. And independently by Salov-Coste, also in 89. And essentially this gives you a bound on the gap, right? So if you bound the conductance, you can get bounds on the gap. So this is a variant of Chig's inequality, but applied to microchains. So it's gap over 2. So what's the point, right? The point is that if we somehow manage to get this quantity, which is not a combinatorial quantity, so it's about sets and understanding the summation and this probability and so on. If we get a handle on the conductance, well, the conductance gives us both an upper bound on the gap and a lower bound on the gap. And since it gives us both upper and lower bound on the gap, it also gives us both upper and lower bounds on the mixing time. Okay, so analyzing the conductance of the chain gives you bounds on the mixing time. And now here, there is something that is quite useful of the conductance, is that the conductance is very good for proving lower bound. Actually, it's a lot easier to prove lower bounds using the conductance than upper bounds, right? Because to prove lower bounds, all you need to do is find a set that has a small conductance, right? So if you get a set that has some, if you get a set that has small conductance, that will give you an upper bound on the conductance of the whole chain. And if you get an upper bound on the conductance, then you're getting an upper bound on the gap, which means you're getting a lower bound on the inverse of the gap. And a lower bound on the inside of the gap is giving you a lower bound on the mixing time, right? So you see, like, there is a disparity here, right? It's a lot easier just to find one set, right, that we think is bad, versus analyzing every possible set, right? So, okay, so let's see, let's do some examples. Questions before we do examples? I think I'll do the random walk on the hypercube just to, because we did the coupling. We have an order n log n bound, upper bound on the coupling, on the mixing time using coupling. Let's see if we can get a lower bound, right? Let's do again the random walk on hypercube. Okay, so remember, what we need to do, and I want to do a lower bound on the mixing time now. What we want to do is find a set with a small conductance. Right? So one candidate here that I'm going to propose is consider the set of all binary strings that start with 1. Right? It makes sense that the chain needs to, you look at all the strings that start with 1, and then you look at all the strings that start with 0. The chain needs to, may have some problems transitioning here, right? Because the only way it can move between starting with 1 and starting with 0 is it really needs to hit the first coordinate and flip it. Okay? Most times it won't be doing that. Most times it will just flipping all the coordinates other than the first one. Okay? So that's the intuition for picking this set. And now, as I said, there is really no, once you pick the set, it's really just a calculation. You just need to compute these quantities, right? First, what is the probability of the set on the stationary distribution? Well, first, I guess I forgot to mention this when we're doing coupling. What is the stationary distribution for the random walk on the hypercube? You know, it's symmetry, right? There is every state has the same out degree. Everything is very symmetric. You can check that the uniform distribution is actually right. Pi is uniform distribution over omega. So this is the stationary distribution. You can check that. You can check even the reversibility conditions, and that holds the ideal balance condition. And that means that the probability of S is just S over the number of strings, which is 2 to the n. Right? So, well, and for us, S is all the strings that start with 1, which means that this is 2 to the n minus 1 over 2 to the n. So this is 1. So that's pi of S. So that's definitely one of the sets that we want to consider. Now, if we look at the conductance of S, this is going to be equal to, okay, we look at the summation or the X is to write this, and Y in S complement, pi X minus Y over pi of S, but this pi of, okay, let's just write it, pi of S, right? Okay, so if we are at X, what are the possibilities from transition into some Y in the complement, right? Well, the only option is really to pick the first bit. That's the only string in the complement of S that we can go to in one step of the chain, right? So there is only one, in this summation here, there is only one element for which this quantity here, P of going from X to Y, is not 0, right? And that is the binary string that has the first bit flipped from 1 to 0, right? Okay, and for that particular string, the probability of that string is going to be 1 over 2 to the n. We saw that, right? It's uniform distribution. And then the probability that we transition, that we actually go from X to Y, well, we need to pick the first bit. That happens with probability 1 over n. And then with probability 1/2, we need to, with probability 1/2, we set it to 0. Okay? And now we saw right here that pi of S is 1. Okay, and now we finish up the calculation here. The number of X in S is 2 to the n minus 1. So you get 2 to the n minus 1 times 1 over 2 to the n, 1 over 2n times 2. And you get all this cancellation. This is 1 over 2n, right? So this is the conductance of S. This means that the conductance of the whole chain, right? The conductance is a minimization over all the sets of probability less than or equal than 1/2. So definitely this is going to be less than 1 over 2n. And with this, we get a bound using this theorem here, an upper bound on the gap, right? We get that the gap of P is less than 1 over n. And using the relationship between the mixing time and the coupling time, this implies that the mixing time is at least n. Okay? So with coupling, we're able to give an upper bound of n log n. With this approach, with the conductance, we were able to get a lower bound of n, which is n log n is the right answer, by the way. So the lower bound is what it's a little off here, but it's a very distant one, right? Now we know that we're only off by a log n factor. Okay, so I'll do one more example, kind of an easy one, because this one, it showcases that we can actually get upper bounds to using the conductance, right? So it's not only lower bounds. In some cases, when the chain is simple enough, we can also get an upper bound at mixing time using the conductance. And for this, consider the random walk on the complete graph, right? By the way, are there questions here? You guys are now more quiet. I guess some people have left, but you guys have questions, or feel free to interrupt me. I'm rushing through this, but there's no point in rushing. I can stop and answer questions. No? Okay, so let's do this example and wrap up. This will take just a few minutes. So this is the random walk on the complete graph. So you have a graph, all the edges are there. Within every pair of vertices, you have the edge. And right, so we want to bound the conductance of any set. And in this case, we can really get a close expression for the conductance of any set, and then for the conductance, right? Because there is a lot of symmetry. When we look at S, right? So what is this? This is the summation over X in S, Y in S complement, pi of X over pi of S. Right, okay, so for every vertex in X, okay, so first the stationary distribution is a uniform one, right? So pi of X is 1 over n, and then pi of S is S over n. Again, by symmetry, everything is symmetric here. The uniform distribution is the stationary distribution. And the probability that from a set X we go to something in the complements, remember that we're picking a random neighbor, right? So you have from a vertex we have n-1 possible choices, right? And the probability that we go to S complement is just, well, the size of S complement over n-1, right? So this is the summation over X in S. And then for every Y in S complement, okay, probability of X is 1 over n. And for every Y of n S complement, the probability that we go there is 1 over n-1. Every vertex is chosen with the same probability. This is S over n. And what this means is now okay, so the number of x's in S is just S. The number of x's of y's in S complement is n minus S. All of them have the same probability of 1 over n times 1 over n minus 1. And we're dividing this by S. So now we simplify things here, and what we get is essentially n minus S over n minus 1. And this is the equality, right? We really, for this case, we can get the conductance of S, which means that if we're looking at the conductance of the chain, which is the minimization, the minimum corresponds to the minimum S, so that the probability of S is less than or equal to 1/2, right? Well, we know that the conductance of S is just n minus S over n minus 1, right? Which means that this is getting smaller as S increases, but we cannot take S too big because otherwise it will violate the condition that is less than 1/2. So the best thing here is to take S to be any set of size roughly n over 2. I mean, n over 2 is if it's an even, n is even. If not, you take n minus 1 over 2. And then this, once you do that, you get to see that this is roughly 1/2. Okay? And see, here we get the conductance. We really get what it is. It's constant. And because the conductance is constant, this transfers and says that the gap, right, is also constant. Which means then that the mixing time is going to be lower bounded by some constant and upper bounded by the inverse of the gap, which is some constant of 1 times the log of 1 over pi min. But here is the uniform distribution, so pi min is 1 over n. So this is just log n. So So in this case, we can use conductance to get both upper and lower bounds on the mixing time. Okay, so to recap, let's just do a very high-level recap. Design Markov chains to converge to a stationary distribution, run it for a long time to get a good sample. What do we know? How do we know what long time is? There are two methods, probabilistic, and in that case, especially we mean the coupling method. The coupling methods allow you to get a bound on the speed of convergence. There is this other family of techniques that are analytical techniques. The main one considers the spectra gap of the Markov chain. The inverse of the spectra gap is a very good proxy for the actual mixing time. Now, bounding the spectra gaps is a little bit hard. So there are ways for doing that. And the most popular one is this idea of bounding the conductance of the chain. Okay. So any questions about this? Okay, so in the last few minutes, I usually leave you guys sometimes to ask questions, but they don't have to be limited to, I mean, they can be about MCMC research, or how you get started, or how I got started. But you can also ask me about research in general in TCS, or applying to grad school, anything you like. So use this time to ask me questions, and we'll stop after you're done asking questions.
So how did you start studying this or researching this? How did you found that you're interested in all of this on Monte Carlo simulations?
Yeah, that's quite it really happened very ad hoc. So I was an undergrad, and I guess sophomore or something like that, maybe sophomore, junior, I don't remember. But I was one of my peers in this programming team competition. So they told me, yeah, you should start doing research. Right? Okay, so I approached the one faculty that I had taken an advanced math class. It was like a linear algebra class or something like that. This faculty happens to be an expert on MCMC. So, and that's how I got started. Like I started working on MCMC as an undergrad. Then I went to grad school, and there was a faculty there doing MCMC. I really like it. I like randomness. It seemed like a good match, and it really happened because of that, right? So I guess what you should get from this story is that if you're interested in math and computer science, there are many, many interesting things. Most topics are actually interesting, right? Crypto, randomized algorithms, game theory, theoretical machine learning, quantum computing. All these are really fascinating research areas. And if you're curious, you will find interesting problems in any of these areas, right? So, yeah.
Yeah. Can you hear me?
Yeah, go ahead.
Yeah. I wonder whether, would you like to give, some brief example? I mean, I wonder whether MCMC can be used to, construct a approximation algorithm.
Good, right. So there is this, this is a very active area of research, and one that this is really core to my research, that is this counting problem. So I think back at the beginning of the first lecture, I told you this idea of finding the number of independent sets of data, right? That's a counting problem, you're counting, right? Or finding the number of colorings or proper colorings of data, again, you're counting, right? So doing this exactly, these are sharply hard problems. Now you can ask the question of, can you do those approximately, right? Can you approximate the number of independent sets? Can you approximate the number? And of course, these problems sometimes are hard, sometimes are easy in terms of that you can solve it in polynomial time. And there is this famous reduction of Jerome, Valen, and Basirani that says that if you can do approximate sampling, you can do approximate counting for a very large class of problems, for set-reducible problems, right? So if you can sample, you can count. If you can count, you can sample, right? So in our community, you interchange between the two, right? If you can count, then you can sample. If you can sample, you can count. Right? Now, MCMC is a very powerful approach because it gives you sampling algorithms, and if you can sample, then you can count, right? So you get a host of approximation algorithms just from knowing how to sample.
Okay, so MCMC So basically you have said MCMC has a, a variety of expectations on approximate counting, right?
I don't know what you say, expectations. It's
No, application, sorry.
applications. Yeah. Okay, yeah.
It just
But yeah, MCMC has lots of applications on approximate counting, but that's one of the applications of MCMC, right? Because the sampling problem itself, it's really perhaps even more popular in applications than the counting problem, which is very relevant in TCS and discrete math. But when we're doing applications, people really care about sampling from this statistical physics model or from these machine learning models. And they use MCMC, and in most cases they don't have theoretical guarantees. I mean, in some cases they do, but in many cases they don't. So we want to give these theoretical guarantees. So Dustin had a question in the chat. I don't know if Dustin's still here. I guess he left. Okay, so he can ask one of the PAs. Okay, any other questions?
I took a principles of operations research class, and we talked a little bit about the birth-death process, which is sort of related. One of the throwaway lines is that it's very difficult to look at not steady state probabilities. Is there any use or any applications of looking at non-steady state probabilities in Monte Carlo simulations?
Right. So this is a different kind of another area of where Markov chains are useful, right? And it's this idea that we don't look at these ergodic chains, right? Look at chains that have different properties on the state space and have like absorbing state spaces of multiple stationary distributions and so on, right? And there is definitely research and theory in understanding that behavior, right? Like what are the different absorbing states, what are the different stationary distribution, and so on. It's a little bit outside of TCS, and this is completely artificial breakup, right? I mean, this is just that people in operation research and in some engineering areas care about that type of questions. And we in TCS, not so much, okay? But yeah, it's definitely a valid research area, understanding. There is a third one that is actually quite useful for, say, in statistical physics and in computational biology, is that you use the Markov chains as models, probabilistic models of some processes in nature, right? So there is this random process of a particle moving, right? And you look, oh, this looks like a Markov chain. Let's try to mimic that behavior with the Markov chain. And there is a whole branch of research that is like, how can I design a Markov chain that is close to modeling that, that real process, right? And that's a different area, right? Not really quite what we did in these two lectures, which is mostly concerned with algorithms, right? Okay, I see that Dustin is back, right? Yeah, Dustin, so what is the question? The question, well, random walks are Markov chains, right? So, and when we're doing random walks on expanded graph, you're just looking at Markov chains on a particular types of graph, right? So definitely, maybe what you mean is that, that you get this analysis of the eigenvalues of expanders, and in expanders, you get that these Markov chains are moving fast, right? Because the whole notion of expanders is that there are no bottlenecks, right? So if you have a set, you have a lot of edges going out of it, which means that you're never going to get stuck in the set, right? So expanders are graphs where the random walks are quite fast, right? So the Markov chains are fast. So that's probably why you see some connections between what you were doing with expanders and Markov chains. It's just a special case of fast Markov chains. Hope that answers the question. Anyone else? Any other questions? Cool. Okay, so you have some problems on coupling, some problems on conductance that I left with the TAs. Feel free to email me if you want to follow up with some questions about MCMC. This is a very short introduction. So if you have questions about some proofs, some research directions, feel free to reach out. Okay.
Thank you so much. It was very informative lecture.
See you.
Thank you.
Bye.